Navigating the Quantum Realm. Wave-particle duality unveiled. 1. Introduction. Quantum conundrum. The concept of wave-particle duality stands as a cornerstone in the edifice of quantum mechanics, challenging our classical notions of particles and waves. In this exploration, we delve into the fascinating realm where particles exhibit both wave and particle characteristics. 2. Historical roots. Some text goes here wave or particle. The journey into wave-particle duality begins with the early pioneers of quantum theory. Thomas Young's double-slit experiment in the early 19th century laid the groundwork, revealing the wave-like nature of light. Photoelectric effect. Albert Einstein's explanation of the photoelectric effect in 1905, where light behaves as discrete particles, photons, added a particle dimension to the evolving quantum narrative. 3. The double-slit experiment. Unveiling duality. The iconic double-slit experiment is a key to understanding wave-particle duality. When particles, such as electrons or photons, are sent through two slits, they create an interference pattern on the screen, suggesting a wave-like nature. However, the particles hit the screen as discrete entities, behaving like particles. Observer effect. The act of observation itself alters the outcome, blurring the line between particle and wave behavior. This phenomenon challenges classical intuitions, introducing a level of uncertainty inherent in the quantum world. 4. De Broglie's hypothesis. Matter waves. In 1924, Louis de Broglie proposed that if particles exhibit wave-like properties, then perhaps matter, like light, can behave as both waves and particles. This daring hypothesis opened a new chapter in our understanding of the dual nature of entities at the quantum level. Wavelength of particles. De Broglie introduced the concept of the wavelength of matter waves, inversely proportional to the momentum of a particle. This wavelength becomes significant in the context of interference and diffraction phenomena. 5. Heisenberg's uncertainty principle. Limits to precision. Werner Heisenberg's uncertainty principle, formulated in 1927, complements the idea of wave-particle duality. It asserts that certain pairs of properties, like position and momentum, cannot both be precisely determined simultaneously. This inherent uncertainty underscores the probabilistic nature of quantum entities. Quantum weirdness. The uncertainty principle challenges the classical notion of a deterministic universe, emphasizing the inherent fuzziness and unpredictability that govern quantum systems. 6. Schrödinger's wave equation. Quantum wave function. Erwin Schrödinger's wave equation, developed in 1926, provides a mathematical framework to describe the behavior of quantum particles. The wave function captures the probabilistic nature of finding a particle at a particular position. Probability clouds. The solutions to Schrödinger's equation result in probability distributions, often depicted as three-dimensional clouds. These clouds represent the likelihood of finding a particle in different regions of space. 7. Experimental confirmations. Electron diffraction. Subsequent experiments, such as electron diffraction, have confirmed the wave-like nature of particles. Electrons, when directed through a crystal lattice, create diffraction patterns analogous to those produced by waves. Wave-particle duality beyond light. While wave-particle duality was initially associated with light, its applicability extends to matter particles, including electrons, protons, and even large molecules. 8. Quantum entanglement. Entangled particles. Wave-particle duality intertwines with the phenomenon of quantum entanglement, where particles become correlated in ways that defy classical intuition. Changes in the state of one entangled particle instantaneously affect the other, irrespective of the distance between them. Non-locality. Entanglement challenges our classical understanding of locality and separability, introducing a level of interconnectedness that transcends traditional boundaries. 9. Philosophical implications. Nature of reality. Wave-particle duality prompts philosophical reflections on the nature of reality. The concept challenges classical realism and determinism, inviting us to embrace a quantum reality characterized by inherent uncertainties and probabilities. Observer-dependent reality. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, propose that the act of observation plays a fundamental role in defining the reality of a quantum system. 10. Conclusion. Embarking into the quantum abyss, wave-particle duality stands as a profound revelation in the quantum journey, where particles and waves dance in tandem, defying classical expectations. As we navigate this quantum abyss, the duality concept invites us to relinquish our classical intuitions and embrace the intrinsic uncertainties that define the captivating and elusive nature of the quantum realm.